Hello everyone and welcome to the start of a series where I make a robotic arm and you get to watch my failures. So basically a while ago I bought a 3D printer and I was like, oh, that's cool. I already have one. So I was like, what can I do with these parts? And there are a bunch of steppers, there are like a couple circuit boards and Arduino, and I'm like, oh, you know what I'll do? I'll make a robotic arm because I can do that with these parts that I have left over and like my current 3D printer, right? So I set out to start doing it, and pretty soon into it, I came across a problem. You don't actually get much force out of a NEMA 17 stepper motor. They're actually fairly weak, and you go like, oh, but they're using 3D printers. Well, yeah, because in 3D printers, there's very little friction that you're dealing with. Like, you're not like slowing this thing down. It's just going. There's very little resistance, and all it has to do is be able to travel. But when you want to do a robotic arm, you have to lift things, and you have to account for the weight of the arm itself and everything that you're trying to lift on the end of the arm or whatever application you have for it. So the first thing that I set out to do, and the first problem that this video will address, is how do I turn a NEMA 17 stepper into a more powerful motor that's essentially, or not more powerful motor, but how do I increase its torque, right? And essentially, okay, you have to find a good balance between a high torque and a high speed. And I essentially ignored the speed aspect of it and decided that all I need right now is I need to make sure that I can lift things with this robotic arm. So as I was designing the robotic arm, I created some requirements for it, in which I basically said that it needs to be able to do several things. And one of those things was lift 5 pounds at the end of a 2-foot range, which is what I just decided I wanted it to be, right? 2 feet, that's basically the length of most of my arm, so that's kind of what I'm going to do. I did some math, and I found out that I need a reduction of roughly 60 times to be able to get a NEMA 17 stepper to achieve that full torque that I need to be able to lift something at 5 pounds. And to clarify, this is for the second axis of the robot. So if axis number 1 is rotation around a base, this is axis number 2 that determines the forward and backward motion of the shoulder. So I set out to create a gearbox that has a reduction of at least 60 times. And my hope was to get it with a reduction of more than 60 times, right? So I have some overhead. And I was like, 150% seems like a good overhead to have. So I will try and get one with 90, a reduction of 90 to 1. And I set out trying to find a gearbox that can do that, and there are none. So this is the process of me creating this gearbox and the one that I have printed right here on the end of my NEMA 17 stepper. So my methodology for creating this was I need a gearbox with a really high reduction ratio. And there are several gearboxes that can achieve really high reduction ratios. They include cycloidal drives, planetary drives, and harmonic drives. But one of the criteria that I specified when I started this project was that this would be easy to make, right? This arm would be like anyone who wanted to make it could be able to do it in $200 or so, right? You just need to buy the parts and you need to be able to 3D print the casings and any like specialty parts for it. But most of the things should be generic. So starting with that, I decided, okay, well, harmonic drives are immediately out. They require a flexible spline to be able to rotate around, and you can't make a flexible spline on a 3D printer accurately. Sure, you can play around with flexible filaments, or you could play around with nylon, or maybe some really thin ring gears, but the chance of that breaking is extremely high, and the chance of you even being able to print with such flexible filaments is unlikely that it will turn out as an accurate print, which is unfortunately what you need for gears. You need pretty tight tolerances because you don't want a lot of backlash in them. So that disqualified that gearbox. And the second gearbox that I could have done was cycloidal. And cycloidal is really nice. It's back drivable. But the problem with cycloidal is that it requires a lot of extra parts. You need a lot of bearings, you need a lot of metal rods to allow the center to wobble around on. And that's just not something you really want to do with 3D prints, especially if you want to keep the amount of external parts that you need on a print to a minimum. But there is one gearbox that you can make with absolutely no external parts, and that's the Planetary Gearbox. Because all it is you don't need bearings, you don't need any of that. You can just have 3D printed gears. So that's the one I went. So looking up high reduction planetary gearboxes for NEMA 17 stepper, they all seem to max out at around 17 or 20 to 1, right? So that's not going to work for me. I need at least 3 times that, preferably 5 times that. So I set out to create my own. And while I was doing this, I came upon a video from Levi Jansen. I'm sorry if I butchered your name. I'm really sorry about that. Who basically was talking about a gearbox that I'd never heard before. It's called a split ring planetary gearbox. And the split ring planetary uses like a combination of 2 planetary gears to achieve really high reduction ratios. So when I saw it, I had an aha moment. I was like, okay, good. This is the one that I'm going to design. So I got into it, and the basic principle is that you have 2 rings. The bottom ring and the top ring have a small difference in the number of teeth that they have. And with this small difference, you are able to achieve really high reduction ratios, because as the sun gear turns, it turns the planets on the bottom ring. And those planets are slightly misaligned with the top ring gear. And as those planets make one full rotation, they align the top planetary ring with themselves, which result in really, really high reduction ratios. And I basically started designing it with 2 times the gear reduction that I wanted. So 120 to 1, or I think in my case I had 123 to 1. And basically what I ended up with is this design right here. And breaking it down part by part, we can see that it has the bottom ring gear, which is part of this housing for a stepper motor, or this part right here. Then we have a sun gear and 5 planet gears. So this is a disassembled one. Granted, it doesn't have all 5 planets in there, but we have a sun gear, 3 planet gears on this one, but 5 on this model here. We have a planet carrier for this, which I have right here. So the planet carrier holds them all in place, and you can see that it's on the smaller ring gear. And then finally, the top ring gear covers it all. And just like that. So upon turning this bottom sun gear, these planets turn and align the top one to themselves. So you can get really high reduction ratios. And that is exactly what I have right here. And this model came out wonderfully. It has an extremely well-built assembly, and there's basically no backlash in this at all. As in, I can try and turn it as hard as I want. There's nothing connected to this motor. So this is the motor just sitting. It's not back drivable at all. So if you had a scenario where you wanted the robot arm to hold stiff, this would be able to achieve that. It's essentially immovable in its position, which can remove some functionality if you wanted to position the arm, say, in a very specific place just by moving it with your own hands. But that can be compensated for later in software, where there will be an interface to allow you to move the arm to that specified location. But there's basically no slack, even when I am absolutely like really trying to wrench down on this. So that's great, and it runs extremely smoothly and extremely well. Also, the parts just slide in and out, so they are really, really well built. And the offsets of the top planetary gears is a really unique thing to this gear set, because as you can see, this planet has its teeth in line, but this planet does not. You can see that its teeth are separated. This is one part of a bottom tooth, and this is the top part of that same bottom tooth. You see that this one isn't exactly aligned either. We have the top section here, the bottom section there. So you need to make the two rings mesh independently of one another, which introduces some problems in CAD modeling because it's really hard to get that angling down. But one of the ways that I found to get around this problem, if you want to design your own split ring planetary gear set, is what you need to do is get the two drawings of the gears, the two sketches of the gears, and extrude it out, put it in an assembly, place the top ring gear on top of your, so basically make this assembly right here, insert the top ring gear onto this assembly, and then individually go and edit each of these pieces to make the top mesh with the sun gear, the top ring gear. And by doing that, you can easily get that angle you need without having to do any math on it. In fact, I didn't do any math on it because I don't even know the math that it requires. So if someone does know the math, feel free to let me know, and I'll be more than happy to congratulate you on that, but I will not be doing that math myself. So here I've got my NEMA 17 stepper with the gearbox completely assembled onto it, and it's got a really snug fit. There's holes in the bottom for screws to connect to the NEMA, even though mine isn't perfectly accurate due to some warping when I printed it, but that's beyond the point. So I'm going to go ahead and plug in my Arduino, which you can't see because it's sitting on the floor right now, but I'm going to go ahead and plug that in, and we should see it start turning. So the Arduino is plugged in, and we should see this start turning soon, hopefully. Oh, there we go, and it's turning. So you can see that even though the planet carrier in the center is spinning around decently fast, the outside planet gear is spinning around incredibly slowly. So I have the stepper running at full speed, and I'll show the code on the top in a second, but basically this should be moving as fast as it possibly can, but this top gear is barely turning, which is exactly what I want for the robot arm, because realistically it would never have to complete a motion of more than, say, 90 degrees. But this is incredible. This is exactly what I want. The only changes I would ever make to this is some way to keep the top pressed down more, but other than that, it's amazing. Like, I can try and stop this, but it is, yeah, it's not stopping. There's some grinding in there. I haven't lubricated this at all, and these gears are fresh, so they've never run before, so there might be slight intolerances between them. But if I let this run for a little bit, these should grind themselves down to smooth, and if I add some WD-40, they should be more than ready to go. But yeah, it's an incredible little gearbox in such a small space to achieve such a big reduction, and to work so smoothly too. It's just I find this fascinating. But yeah, this is episode 1 about the about building the robotic arm, and yeah, I hope you guys enjoyed seeing this gearbox, and feel free to help with the project or take a look at the files that I've provided in the GitHub description below. I guess this was gonna become a blooper, but you can see how smoothly it's turning here. I'm keeping my hand there to prevent it from shooting off because I have not created a case to hold this down onto it. That is the next step. Maybe 2 screws going into the sides to hold it down, or maybe in the corners. But yeah, it's so incredibly smooth, especially for something that has like literally nothing other than 3D printed parts. It's quite incredible, and these parts have no finishing on them. They're just regular PLA parts. So yeah, feel free to print it and let me know what you guys think about it.